a natural gas star AO system for GMT, some performance analysis and simulations that we have done at GMT. So first I'm going to briefly describe the GMT design for those of you who are not familiar with it. Then I'm going to talk about the GMT adaptive optics architecture, which is based on an adaptive secondary mirror, and the Wavefront sensor suite that we have to do wavefront control. Then I'm going to focus on the natural gas star AO and system and present some simulations and the performance that we have obtained. And more interestingly, perhaps, it's how all this, how the adaptive optics system will interact with the active optics and phasing. And I will present some simulations regarding that as well. And finally, some summary and conclusions and further work. So as you may know, the GMT is a 25-meter diameter ELT. It is a doubly segmented design. It has 7 large segments. Both primary and secondary are segmented, and the gaps are quite large. The ones between the inner segment and the outer segments is 40.8 centimeters on axis, and among the outer segments is 34.5 centimeters. So the GMT adaptive optics architecture, it's based on an adaptive secondary mirror that it's used for providing wavefront correction to all the focal stations. Then we have an important sensor, the acquisition, guiding, and wavefront sensing system that it's quite complex. It's the one that will be performing all active optics and phasing using 4 probes that I will describe in a dedicated slide. And the other wavefront sensor that it's relevant to AO, it's the actual AO wavefront sensor that has 2 options: a natural gas star wavefront sensing system and a laser tomography wavefront sensing system. I'm going to focus on the NGWS only. But the important thing here is that to note that all the after reflection from the tertiary, the light, the infrared light will go to the instrument, while the visible will be reflected, and except the ones that goes to the LTWS will go to the NGWS, which is based on pyramid wavefront sensor. So just very briefly, in the NGS AO mode, the AGWS will control telescope pointing, collimation, and M1 figure. So even if this will be done before the AO loop is closed, we have to keep these loops active because they will ensure that the evolving M1 errors will be corrected at M1. And I will explain with some examples how this will be done. And then we will have the NGWS control that will provide a correction on axis, and this will include segment phasing. So the NGWS will have to control in real time the segment phasing of the full optical train by applying segment phasing corrections directly on the ASM. It's important to note that the LTO architecture is very similar, except that the LTWS cannot measure segment piston, so that error term will remain uncompensated, the atmospheric turbulence piston.
Excuse me, when you talk segment phasing, do you talk which segment? Is the secondary segments or the primary segments or the combination, like the two phasing?
Exactly. So what is important for optical quality is that every pair it's controlled to the right separation. But for field-dependent control, then the full train should be all phased together. So by using this combination of wavefront sensors, both the NGWS and the AGWS, as I will show in the incoming slides, you can ensure a good collimation, a good alignment, good phasing for an extended field of view. So the AGWS has 2 channels. Remember that there are 4 probes that are identical, and each of these probes have 2 channels. One visible channel that will be used for all the, in particular, the important thing here is it will be done for active optics and sensing. So they have 2 different Charcot-Maries, one with 124 and one 48 by 48 subapertures, as shown here. And there will be an infrared channel that is operated simultaneously with the visible one in J-band using a CRED 1 camera, so it's a fast readout that will be responsible for providing phasing measurements at off-axis angles. So this sensor basically, it's based on a dispersed fringe sensor, so it works like a Jones slit, double slit, and that pattern is further dispersed on the vertical direction as shown in this animation. By taking the Fourier transform of this fringe pattern, which actually in this simulation, it's in this measurement, actually this is a real measurement with a prototype of this device. The fringe pattern starts to rotate as segment piston increases between 2 segments. And the data processing actually does not deal with the fringe rotation. We could do that, but we don't do it. We perform an FFFT on the fringe pattern to get the kind of image that you get here, and the displacement of the side lobe by estimating that displacement with a simple centroid or some more complex fitting algorithm, we can determine what is the differential piston at this subaperture. So by combining the measurements from all the 12 subapertures that are bridging the gaps between the segments, we can estimate the differential piston of outer segments with respect to the central one.
Just to get an idea, for this 45 degree rotation, do you know how much is the differential piston?
This one is at the, it's getting like a half of the limit range. So this would be like 15 microns, because the capture range is 40 microns. So then we have the NGWS that is based on actually 2 pyramid wavefront sensor channels. The first one is the one that provides the AO correction plus phasing, but because it has a limited capture range, it's not 40 microns as the DFS. This one, it's limited to half a wavelength, plus minus half a wavelength. So it's it was found during the preliminary design study that a second wavelength, a second channel operating at a slightly different wavelength, like 100 nanometer separation, would provide that information that was needed to extend the capture range of the pyramid wavefront sensor up to 4 microns. So that was at least considered enough to operate in some given observing conditions, as I will show in the following slides. The important thing to say here is that it has a sampling of 92 by 92 subapertures, and it uses first light OCAM2 cameras. Oh, sorry, and this is an actual pyramid that it's being tested at Archetri. So now, regarding simulations, at GMT we have been building for quite some time complex machine, a GMT integrated model that will simulate structural dynamics, optical propagation in real time, and what concerns to this talk is that this it's an important feature to take into account in these simulations, because since we want to test the performance of wavefront sensors operating at different angles, and we want to measure what are the optical effects of moving optics at M1 and M2 position. This is the only way to capture in real time in a simulation the effects in the field. One further detail regarding the modal basis for the AO system. At PDR, we were considering global modes, which is nice because you have the control of global tip tilt, which is an important mode to correct properly. But segment piston, which is also important to correct, was not possible to control directly because it's not an orthogonal norm mode on this modal basis. It was expressed as a linear combination of a large number of global KL modes. We are currently exploring the possibility to use a segment KL modes basis in which segment piston and segment tip tilt can be directly controlled, and so they are ad hoc controller can be designed for those, and the simulations that I will present consider this kind of modal basis. Further, it will allow us for A operation with a reduced number of segments, because at first light we are considering having perhaps only 4 segments out of 7. And it will also allow for an optical calibration of modes independently. Some further details, because the segment KL will only cover a portion of the pupil, then the signals from all the other subapertures will only contain noise. So this, in the acquisition of the interaction matrix, care has to be taken to only take into account those subapertures that contain useful information. So masks have been designed to obtain and collect only those subapertures that are pertinent to each segment, and similar to segment piston, in which signals are very localized at the gap. And so in order to reduce noise propagation, also masks have been custom made for this purpose. We can see here the SVD of the NGS AO, and the last mode, it's interesting to see that it's a global piston, but without the central segment, because that's our reference. So we do control this mode, but it has simply lower sensitivity. These are simulation results. You can see in the first plot the wavefront pair segment, how it converges. So because, well, in the first plot, you can see the wavefront error per segment, how it converges to 0. There is no, the mean value has been subtracted. This is why you see that it converges to 100 nanometers. Whereas on the plot on the right, you can see the segment piston, how it converges to multiples of the wavefront sensing wavelength. And this is just because at closure, the atmospheric turbulence projected on the GMT pupil will produce segment piston errors that are several microns in amplitude peak to valley. So, and this of course increases with the sync conditions. So it is almost a fact that the NGS system will dephase, let's say, the telescope at closure. This can be mitigated by some modal bootstrap strategies that can be developed and so on, but it is a fact that it will happen. And this is one of the functions of the second wavefront sensing channel, in which by taking measurements at a slightly different wavefront, wavelength, it can disentangle those segments and bring them back to 0. So after this is done, and this is represented here in a very fast way, this is not actually done like that. It's more, it takes several steps, but for the purpose of this simulation, I just did it in one stop with a fake sensor. The point here is that I wanted to see what is the residual performance after it has converged, and you can see that then the pyramid wavefront sensor, once the segment have been recaptured, it maintains the phasing to 125 nanometer RMS, and the wavefront error overall is 90 nanometer RMS. Now, these are results from the PDR that was finalized in 2013 by the Archetri group. I was there at that time. And it considers a wavefront sensing in the R plus I band. And this plot is very interesting because it shows that as seeing gets worse, and in this case, in fact, the plot starts with a bad seeing conditions improving and then getting worse again. You can see that this phenomenon of losing segments, increases. And of course, the second wavefront sensing channel will recover them, but we would like to find a solution in which stability is further guaranteed instead of having two channels in which the second channel actually tries to undo what the first one, the errors of the first one. So it's not easy to do that, obviously. But one simple solution, simple in concept, not in practice, will be to consider doing the wavefront sensing at longer wavelengths. Of course, this is not the architecture of the GMT AO, but if we find that this is really the way to guarantee that, that's an alternative that we are considering. And now, very fast. Okay, I'm going to just mention briefly that while the AO will control the wavefront on axis very well, and it doesn't matter if the errors are on M1, on M2, the on-axis performance will be corrected. Off axis, there will be an aberration because, for instance, in the simplest situation, when you have an M1 tilt compensated by the M2, this mode will generate in the field a field-dependent segment piston that will increase linearly with the field. So we have devised a strategy to mitigate these problems by using the AGWS, controlling M1 aberrations at M1 by using those measurements. And we use both the signals produced by the Shakarmans and the dispersed fringe sensors together in a strategy that we have called the merge reconstructor. And you can see here that in this case, all the upper plots represents M1 bending modes, errors that are being compensated on the lower plot. On all the lower plots, you see the KL modes, the AO correction per segment. You can see how those aberrations on M1 are compensated on axis by the KL modes. But every iteration that you see there, it's the AGWS that is removing the aberrations on M1 so that the M2 is slowly also converging to zero until all aberrations at M1 are removed. And so in this simulation that there is no turbulence, just for clarity, you can see that everything converges to zero. The same happens with the field-dependent segment piston, which is produced by an M1 segment tilt compensated by the M2 segment tilt. So M1 segment tilts are corrected. And so finally, we have the conclusions. We have, through simulations, obtained that the NGO performance is stable in the 95% of sync conditions, so below 1.1 arc-second sync. And that we are working on the interactions between several AO active optics and phasing loops with the high-fidelity integrated modeling simulations. We are evaluating, we would like as a future work to evaluate alternative second natural Geisler wavefront sensing designs and start evaluating also other errors like wind buffeting disturbances using the integrated modeling that includes telescope dynamics as well. And as a last point, evaluate the NCPA compensation with the NGWS when these aberrations are larger than what the pyramid can normally take.